We want to discuss one remaining aspect of Thevenin's and Norton's theorem, particularly Thevenin's theorem and how it's most often used in power systems applications. Typically, when we have a circuit, one of the main reasons we have a circuit is to deliver some power to a load. So, for example, when you turn your blow dryer on and it gets hot and the motor runs, that's a load, and the power in your home is basically delivering power to that load. Now that's AC. Right now we're talking about DC, but it's basically the same concept. You have some kind of source that is usually modeled as a voltage source, and the goal of that source is to deliver power to a load. But it's not always just as easy as hooking up a source, say a flashlight battery, is just sticking it in a flashlight and modeling that battery as a perfect 1.5 volt source, because that's actually not the way things work. In reality, while we've modeled sources as ideal in this course, in reality most sources are not ideal, and they contain some kind of internal resistance that basically limits the amount of current that can come out of the source. In addition to that, a lot of times, for various reasons, there are other things that are present in your circuit. Other resistors, wires can be modeled as resistances. So when we're actually modeling a system, we get these complicated circuits, and one of the goals in finding the Thevenin equivalent is so that we can have a simple circuit to look at as far as transferring power to a load. So let's look at just a typical circuit, and let me put this up on screen share or on full screen so that I can use the pen. Here's a typical circuit, and what's shown here is a load resistor. So R sub L, that's our load resistor. This little arrow through here indicates that this is what we refer to as a variable resistor, meaning we have some kind of knob or screw that can be maneuvered and twisted, and in that way you're changing the resistance. So that's a pretty common thing. When you take lab, you'll find that you can have variable resistors. These used to be referred to as pots back in the old days. Some people do still call them that. So the reason finding the Thevenin equivalent is important is if you find the Thevenin equivalent, then what you have here is a very simple circuit, basically a voltage source and a resistor delivering power to your load. So that when you calculate the power in the load, that's basically going to be I squared times the resistance of the load, where I is the Thevenin equivalent voltage over the sum of the two resistors. So it's V Thevenin squared over R Thevenin plus R load. This is the current. So I squared R, remember, is the power that's dissipated in a resistor. Now, your textbook and a lot of modern textbooks, because circuit theory has been moved to sort of a co-requisite with calculus, they don't really derive the maximum power transfer theorem in quite the same way. So I will just say that if you actually want to find, so the question is, what is the value of the load resistor that will dissipate the most power? And so, and assuming that V Thevenin and R Thevenin are fixed. So the load resistance is the variable. So you might remember from differential calculus that if you want to find max and min, what you do is you take the derivative and set it equal to 0, and that will give you maximum and minimum points. So what we used to do in circuits class is we would take this equation, we would take the derivative of the power with respect to RL, the load resistance, set it equal to 0 so that we could find the value of RL that gave us the maximum amount of power that was dissipated in the circuit. If you instead just plot this, so they're sort of illustrating this visually, and so if you plot this, you'll see that the power as a function of the value of the load resistance looks sort of like this, and it turns out that if you do that derivative and you set the derivative equal to 0 and solve for R sub L, it turns out maximum power is transferred when RL is equal to R Thevenin. So this is a huge motivation for why we want to find the Thevenin equivalent resistance, is that we then know what our load resistor needs to be in order to draw maximum power. Now, the reality is a lot of times the load resistance is not variable. A lot of times you're supplying power to a load that you don't have any choice over what to set the load resistance. In that case, you often then have to go back to your original circuit and play with that so that you get the load resistor equal to the Thevenin resistance so that you can draw max power. But, that's sort of another circuit design issue. So what I want you to remember is you get max power transfer when R load is equal to R Thevenin. And that's just a very simple theorem. You'll use it now, you'll use it in circuits too. And there's even sort of an electromagnetic fields analogy when it comes to matching impedances that waves see when they travel in media. So this is an important concept about max power transfer. So one thing to point out is that, as we said before, we actually, in the real world, don't have ideal voltage sources, and we don't have ideal current sources. Ideal voltage sources in the real world would have no internal resistance, so we just draw a voltage source, we put plus minus 10 volts, and that voltage source delivers 10 volts independent of its load. It will produce whatever current it needs to produce in order to provide that 10 volts. In actuality, there is some internal resistance in that voltage source. So it's actually an ideal voltage source in series with a little resistor that represents its internal resistance. Same with current sources. Ideal current sources would have an infinite internal resistance. In other words, when you look at a current source, the internal resistance looks like infinity, and so but in actuality it looks like an infinite resistance in parallel with that current source, meaning it looks like an open circuit. In actuality, the current source does not have an infinite internal resistance, so you would see a resistor in parallel with the current source that would represent the non-ideal aspects of that current source. So the Thevenin and Norton circuits sort of show you how that is modeled. All right, I want to switch gears just a little bit and talk about resistance measurement. And I believe in addition to this PowerPoint presentation, I have your project assignment open. So after we complete looking at this picture, we'll then go to the project assignment and talk about the Wheatstone Bridge a little bit more. So the Wheatstone Bridge, one thing the Wheatstone Bridge is used for is it's used to measure resistance. And it's a very accurate method of measuring resistance because you're actually measuring a current when you're using it in this application. The application in the project is actually a strain gauge application, and you're not measuring resistance. There's no galvanometer, so I'll talk about the difference here. So a galvanometer measures current, and in the case of the Wheatstone Bridge, and notice here we show this is another way of illustrating a variable resistor. So R2, this arrow here indicates that you can slide this connector along the length of the resistor, which is usually a wire coil, and that varies the amount of resistance that is between the node here and here, as opposed to just connecting at the end of the resistor. And the reason to sketch this circuit this way is just to illustrate what happens. So basically R1, R2, R3, and R4, if the galvanometer is removed from the circuit. So for the moment, let's remove this guy and just visualize open terminals here. In that case, the total voltage drop across R1 and R2 would be V, meaning V would divide between R1 and R2. And the total voltage drop between R3 and Rx would also be V. And so the total voltage drop would be V, and the voltage drop across R3 would be the voltage divider ratio. The voltage drop across Rx, which is shown as V2, would also be the voltage divider ratio. So if the ratio R1 over R1 plus R2 and R3 over R3 plus Rx, meaning the voltage divider ratio, and you can basically simplify that, and you can say if the ratio of R1 to R2 is the same as the ratio of R3 to Rx, then the bridge is balanced and you have zero voltage between these two terminals meaning if you put a galvanometer here, it's going to read 0 current. So a galvanometer is a current measure. Now, if it's not balanced, then you're going to get some current. So what this figure is illustrating is that basically we have this variable resistor R2 and this unknown resistance Rx. And maybe we can't measure with an ohm meter, maybe we don't have, physical accessibility. I can tell you these kinds of circuits many years ago used to be used to look at things like faults in power lines. And so your resistance Rx here might constitute some really long, like maybe several miles, conductor, and you suspect that it's got a flaw or a fault or a slight open, not a full open, but maybe it's been damaged, or maybe a portion of a grid has been damaged, and you have to figure out where that is. So people used to do, measurements like that back when phone lines were wired and not fiber optic, and they were wired to the home. This was a technique that was used. So maybe it's used in a case where this resistor Rx is physically inaccessible, but yet is still tied to your circuit. So anyway, the way that you determine, for whatever reason, the way that you determine the value of this unknown resistor Rx is you use this variable resistor R2, and you adjust the resistance on R2 until V1 and V2 are equal. Now, when V1 and V2 are equal, there's no current that flows through this galvanometer. Now, because R1, R2, and R3 are known, you can solve for Rx under the condition when there's no current, because then V1 and V2 will be equal. So that was the application of the resistance measurement with the Wheatstone bridge. So you can use 3 known resistors in a galvanometer. You can test an unknown resistor. The unknown resistor is placed at position R4. The variable resistor is adjusted until you show 0 current. At that point, the bridge is what we call balanced, and the voltages from the 2 voltage dividers are equal. So here's the expression in this particular example when you have R3, R1, and R2, and those are all known. R2 has been adjusted so that you get 0 current, and then you can solve for Rx. You can see that by rearranging this equation, Rx over R3 is equal to R2 over R1, or Rx over R2 is R3 over R1. So it's these ratios when they're in the proper ratio and the ratios are the same, the bridge is balanced. So you can talk about the accuracy of the Wheatstone bridge by realizing that any tiny difference in those voltage dividers is going to give you a current flow. So they're talking about reducing the bridge to its Thevenin equivalent. Okay, I don't think that's really necessary, but they are trying to show that even if this is really tiny, that you can still measure a current flow. All right, let's go to your project, because I want to look at the Wheatstone bridge in your project. Now, this is a little bit different, okay? First of all, you'll notice that there's no galvanometer here. Let's see if I can get I don't know if Word's not really great about letting me make annotations in real time. I'll look at my okay. So you'll notice here in the middle there's no galvanometer. There is just a potential difference shown, V sub 0. That's the more common thing, really, is the measurement of a voltage difference. So the first thing is, okay, the bridge is balanced when you have this equation being true. So the ratio of R1 to R4 is equal to the ratio of R2 to R3. In that case, the output voltage is 0. And so this is what they're referring to as V plus. That's what they're referring to as V minus. It is not a problem if the terminals are switched and you've got plus on the left and minus on the right. I have to say, if this were my original write-up as far as this figure, I'd have gone plus minus instead of minus plus, because that's just how my brain works. If you're different by a negative sign, that is probably what you did, is you had your plus and minus somehow flipped with respect to the polarity of the source. That's okay. Don't worry about that. So the project looks at the application of using a Wheatstone bridge in a strain gauge circuit. So what's a strain gauge? A strain gauge it's a metallic device, usually fabricated on some kind of material that can be elongated. It's typically, the strain gauge itself is often metal. It can be stretched, and so as you put force on the metal wire, the force will stretch it, and so the force per unit area is called the stress. The elongation per unit length is called the strain. So delta L would be the change in length, L would be the total length. The strain is defined as delta L over L. Okay, well, as you recall, the resistance of a wire is rho L over A. So if L, the length, changes to L plus delta L, then R, the resistance, is going to change to some R plus delta R. So what that would mean is, in one of these kinds of devices, one of these resistors is going to be changing because part of the resistor is a strain gauge. So in a strain gauge, what is usually done is all of the resistors are assumed to be equal. So you don't have an R1, R2, R3, and R4. You just have R. And then one of them contains a strain gauge, and I think I said in the project you can use the one on the upper right-hand side, but you don't have to, but you can. And so then what happens is, as the strain gauge is elongated, instead of being R, the resistance changes to R plus delta R. So what I want to know is, can you get this delta R in terms of V out R and Vx? So what we really want to know is, can we find an expression for the change in resistance in terms of V out R and Vx? So the way to do this is to take your bridge with your four resistors, R, 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 and R plus delta R. Using circuit analysis, figure out what this voltage is in terms of this input voltage and all the R's. So all you're really doing is you're using letters instead of numbers. How you do this, you can use the voltage divider rule. And so in that case, you would get a voltage here and here. And here. And here. Using voltage divider. So obviously, if these two remain the same, then this voltage would be V excitation. EX is for excitation. V excitation, or V source, over 2 right here. If these were the same, this would be Vs over 2. And you could write, let me change color. You could then write a little KVL equation around here. That would put V out in terms of this voltage and this voltage. So obviously, if all of the resistors were the same, this voltage would be V excitation over 2. This voltage would be V excitation over 2. And this voltage would be 0. If they're not the same, and this one changes to some R plus delta R, then this voltage divider ratio on this side is different. because this one is now R plus delta R. So you plug that into the voltage divider ratio, and you get an expression. You get an expression for this voltage right here, and then you write your KVL around this path, or your mesh around this path, including this voltage drop V naught, and that's what gets you. This voltage will be in terms of V excitation. This voltage will be in terms of V excitation. They'll be in terms of R and delta R, and then this voltage is just your measured value. So that'll give you an expression, and all you have to then do is some algebra. Now, if you make the assumption that R is much, much greater than delta R, and it is in a strain gauge, then you can greatly simplify your algebraic expression to get a solution for delta R. So that's what I want you to do. You'll get down to a point in the algebra where it makes a lot of sense to assume that R is much, much greater than delta R. Then you can simplify your expression and get a very, very good approximation for the change in resistance in terms of the excitation voltage, the output voltage, and the original resistor value. So that's really all you have to do for the project. And then what I did is I gave you some numbers and said assume that your voltage source is 5 volts, and assume that your original resistance is 100 ohms. So what I want you to first show is that when you have no delta R and the bridge is balanced, I want you to show in multisim that the output voltage is 0. And like the previous project, you'll need to have some screenshots of your multisim output, and then you'll need to have some text that says, as can be seen from the output, or from the multisim figure, and if you need to have arrows that point to the figure, the output voltage is 0. Okay, now I want you to assume that we're going to put some strain on this, and the change in resistance due to the strain is going to vary from 0.1 ohm to 1 ohm. What I want to know is what's the resulting range in the output voltage. So you're still going to use multisim. You're still going to look for V out, only now you're going to vary what delta R is. Now, how many points do you need to vary? Well, we're assuming that this is an ideal resistor and resistance is linear, so you actually only need, so that you know what your voltage variation will be, you need to do one run where you let delta R be 0.1 ohm. So that would mean your total resistance would be 100.1. And then you need to do it again where your total resistance is 101. That would be sort of the top limit of the strain gauge. So this project is to get you thinking about measurements. And you'll get some output voltage values. And so what you want to think about is whatever this output voltage that you get when you use multisim, would that be a voltage that you could actually measure? Is it going to be in the millivolt range? Is it going to be in the microvolt range? Is it going to be in the kilovolt range? I mean, and what would make sense as far as if you wanted to actually make a measurement of that? Are microvolts easy to measure? Kind of, but not really. Millivolts usually are a pretty reasonable voltage measurement for most meters and affordable oscilloscopes. So the microvolt or the millivolt to volt range is usually pretty easy to measure. So I just want to know if you introduce this kind of change from your strain gauge, what's your output voltage? And so what this should get you thinking about is, well, what if my strain was much, much lower? What would that mean? What if it was much greater? What would that mean? And so that kind of gives you an idea of kind of how this measurement might go if you were trying to do this in the lab. Now, you'll need to write up your results. You don't need a lengthy report. This is not a very difficult project. It is an individual project. You will need to put your report in Word or PDF form, and we will be doing a plagiarism and academic dishonesty check on this, so this does need to be your own work. I realize that a lot of the problems will be the same, but I mean, a lot of the reports, you should all get the same result because it's not a design problem, so there is a right answer. Now then, for the extra credit, if you want some extra credit, this will probably go, partly toward your, basically it just goes toward your point total. So not the final grade, but my thinking was I would probably put this on exam 1. So if you want the extra credit, you can do that. What I want you to do is play around with the equation for the resistance of a wire, and I want you to find some actual wire information. So you can look up wire gauges. You can assume you have copper, and you can look up the resistivity of copper, and then you can look to see how long would you have, how much wire, what would the length of wire be if you wanted to form a 100 ohm resistor. So once again, the goal of this is just to give you an idea of orders of magnitude and numbers, and using a very thin gauge wire, what would it take to form a 100 ohm resistor. And then once you have a 100 ohm resistor, how much would the length have to increase to get a resistance of 0.1 ohm? Now, if you've got any background in statics or materials or mechanical engineering at all, you may understand that as you stretch a wire, you get this phenomenon called necking, meaning if you visualize stretching a rubber band, when you stretch a rubber band, it gets longer, but it also gets thinner. We're going to assume that we don't have a change in cross-sectional area, and that's a pretty fair assumption as long as the stretching is not too great. And a 0.1 ohm out of 100 ohms, since we're proportional to the length, that shouldn't cause a problem. So it's a decent assumption to make. You pick the material, you can pick the wire gauge. I said take a fairly thin one. That's up to you what you use there. And then think about if, doing something like this would be a reasonable kind of design. Could we use a wire of a thin gauge and a 100 ohm resistor and stretch it enough to get a 0.1 ohm? Would that be a reasonable design to measure strain or elongation? I think you'll find that it probably wouldn't be. There are some other ways that people do this. They basically do something like deposit a copper pattern onto a substrate, and then the substrate flexes and stretches, stretching the wire. They do it in like an interleaved fingered pattern, so that for a little bit of stretch you actually multiply that because the thing zigzags back and forth. So if you're interested in strain gauges and you want to know more about that, National Instruments, which makes LabVIEW and various educational and industrial measurement equipment, National Instruments has a very nice white paper where they discuss measuring strain with strain gauges. So if that's something you're interested in learning more about, you can refer to this white paper. This project reference paper basically does the project for you. So if you can't figure out how to do it, you can go to their paper, and they basically do this derivation. So I guess you could copy that, but that's why I included the reference in case you get stuck with. I know that a lot of people freak out when they have to work with variables instead of numbers. So if you get stuck, this is the project for all practical purposes, and then you can just put that on multisim and simulate. So hopefully this gives you enough information that you'll need to do the project, as well as some definitions on max power transfer. Max power transfer is an important concept, so we will in this week's homework, even though this week is primarily an op-amps week, we will in this week's homework include some max power transfer problems from the previous chapter, because it is and will remain an important topic.